In the main video, the mean curvature is defined as half the trace of the shape operator. But why is it really called mean? This starts by thinking one dimension lower, so we have a curve on a flat plane. We can still define an analog of the Gauss map that extracts the normal vectors, and we can still define an analog of the shape operator. Just as a reminder, the shape operator describes how the change in location on the curve leads to a change in the normal vector. Because we are one dimension lower, instead of a tangent plane, both the change in location and change in normal vector lie on the same tangent line instead. And instead of a 2x2 matrix for a surface, it now becomes a 1x1 matrix, which is just a number, and we directly call this number the curvature of this curve at that red point. This number can be calculated as follows. Let the change of location on the left be a unit vector v, and then apply the shape operator to it. Then the curvature is simply the dot product of v and s of v. This works because s of v is by definition the curvature times v, and v is a unit vector. Now go back to the case of a surface and consider a cross-section. This cross-section is vertical in the sense that the normal vector lies on this plane. How do we determine the curvature of this cross-section at this red point? Well, from our previous discussion on the plane, it should be v dot s of v, but the s is the shape operator on the cross-section. Can we relate it back to the shape operator on the surface? Well, this should be just projecting the shape operator on the surface back onto this cross-section. Luckily, every time when we project S surface of V onto the cross-section, it must align or anti-align itself with V. Why is it always the case? Comment below as an exercise. It has something to do with the fact that the normal vector lies on this cross-section. Anyway, the upshot of this is that S cross-section V is actually the projection of S surface V onto V itself. Therefore, the dot product actually equals V dot S surface V. It turns out that if we take the average of these curvatures among different cross-sections, then we get half the trace of the shape operator of the surface. So it now makes a lot more sense why this is called mean curvature. But why does taking the average give half the trace? In general, when we want to take the average of a function f of x from a to b, we should integrate f of x from a to b, then divide it by the range b minus a. If you want a bit more explanation why this is the case, I made a video about this 3 years ago. If we go back to taking the average of curvature of cross-sections, we can first parameterize the unit vector v as cos theta sine theta, and the shape operator of the surface as a, b, c, d. Then to compute the average, we should integrate the cross-sectional curvature and then divide it by 2 pi, which is the range of theta. The integrand might look intimidating, but it is really just a dot product. You can pause and verify this if you want. The next step is to realize that sine theta cosine theta in the middle is actually half sine 2 theta, which will vanish after integrating from 0 to 2 pi due to periodicity of sine. On the other hand, when integrating both sine squared and cosine squared from 0 to 2 pi, we have pi. So this average equals half of a plus d, which is half the trace of the shape operator. This is why it makes sense to call this quantity the mean curvature. Technically, you can try to deduce this half trace without going through the computation, and it will involve the intuition from my previous video from trace. Again, let's see if you can explain it this way in the comments. As usual, like the video and subscribe. See you next time!